Okay, so welcome to section 9.2. In this section, we're going to take a look at something called measures of variation. And the idea behind measures of variation is in section 9.1, we took a look at measures of center. And in section 9.2, we're going to say, okay, it's great that you can say that the middle is here, that the center is there, but is the data really tightly clustered around that? Or is the data really spread out? And what the idea here is that the measures of variation are going to be able to distinguish between two different data sets. And that if something has a small variation, that means that the data is tightly packed around that center, whatever that center is. And if it has a large variation, then the data would be really spread out. A challenge we're going to have is that these two words don't mean anything. And what I mean by that is 100 a small number or is 100 a large number? Well, it's really going to boil down to what's your center? And then we can talk about it. Okay? Because there are some situations where, and let's just make this a simple thing, money. There are some scenarios where $100 is a lot of money, and there's other scenarios where $100 is almost nothing. Right? If you're going out to dinner, and the difference between two places where you're going to go have dinner, if you have two options, and the difference in price is $100, well, then one of them is clearly very expensive, and one of them is clearly less expensive, and that's a lot of money. If you're shopping for a new car and you've got it narrowed down to two cars and one of them is $100 more than the other one, then that's almost nothing because the size of that value, that measure of center compared to that variation. All right, so in this section, we're going to take a look at measures of variation. So we're going to talk about the range, we're going to talk about the variance, we're going to talk about the standard deviation, and we're talking about how to approximate a standard deviation for group data. That's what we're going to do in this section. We're going to measures of variation. Okay? The range is going to be the first one we're going to take a look at. It is the easiest and possibly the most useless description of variation. It doesn't make any concessions for the relative location of the data points. It doesn't care whether things are spread out or not. The range is just simply the largest data point minus the smallest data point. So here's our first example. We'll take a look at it. Here is a, what is this? Oh yeah, that's right. This is a histogram. Our horizontal axis is the age in years. Our vertical axis is a frequency. So this is a frequency histogram for the bride's age at first marriage. And then we'll take a look at this horizontal axis and we'll say, what is the range of this data set? Okay. So the way I find the range is I take the maximum data value minus the minimum data value. So I'm going to go over here to my graph and I'm going to say it looks like the largest data value is 34. It happens to have happened 3 times, but I really don't care that it happened 3 times. I just know that my maximum is 34. My minimum data value, if I go over here, it looks like my minimum is going to be 24. It happened twice. Again, I don't care that it happened twice. I just know the smallest number is 24. And so then 34 minus 24 gives me a 10. And so I have a range of 10. I don't know whether that's a big number or a small number because I don't have anything else to compare it to, but what I can tell you is the difference between the bottom and the top, between the highest and the lowest, between the smallest and the largest, we have a range of 10. Right? And in this case, since my horizontal axis is measured in years, this would be 10 years for our range because the units of measure on the range are the same as the units of measure on the data points. Okay. All right, let's look at a more encompassing, let's call that, measure of center. And that's going to be the standard deviation. But in order to get to the standard deviation, we first have to walk through some steps. First off, deviation. Right? By definition, when we talk about the data sets and statistics, The deviation of a data entry X is the difference between that data entry and the mean. Okay? For example, if I told you that I had a data point out there and that data point was 16, and I told you that that data point came from a data set where the mean was 12, then the deviation for data point X1 would be 4, because it is 4 larger than the mean. The way that I find the deviation for a value is I take that value and I subtract off the mean. So the deviation for 16 would be 16 minus 12, which would give me a positive 4. Now keep in mind that this formula then would imply that if you had smaller than average, like if you had an X sub 2 that was a 10, then the deviation for X sub 2 would be a negative 2. Because the formula would say to take that 10, subtract off that mean, and 10 minus 2 is negative 2. The sign matters because the sign tells us whether we are larger than average, larger than the mean, or smaller than the mean. All right, so our job is to determine the measure of variation or the variability in a data set, and we're going to use the deviation. And what we're going to do is we're going to take that deviation, we're going to add up all of the deviations for all of the data points in the data set, and then we're going to calculate something called the sample variance. Now, all the sample variances, and I'll highlight it here and we'll talk about the formula. This is the formula right here. Okay? All the sample variance is it takes every deviation, that deviation is that little piece inside of there, and then it takes all of those and squares them. Now, the reason we're squaring everything is it's going to take all of the numbers, whether they are positive or negative to begin with, and make them all positive. And then it's going to add up all of those values. And once it adds them all up, it's going to divide by n minus 1, n being the number of data sets. And we're going to get something called the variance when we do that. And then we're going to turn the variance into the sample standard deviation, or the standard deviation, by just taking the square root of that variance. So you notice that that formula right there is the formula we just talked about, just under a root. So we squared and then we unsquared. Right? We squared to make all the positives and negatives just be all positives, and then we unsquared to get back. All right, so let's take a look at what this really means. Here I got an example. Okay. I have a study here of high school football players that suffer concussions, and researchers placed the players in 2 groups. Players that recover from their concussions in 14 days or less were placed in group 1. Those that took more than 14 days were placed in group 2. Here are the recovery times for group 1. Find the standard deviation of the recovery times. So I've got to do this for this data set. Now, something that isn't stated but is hidden in there is that inside of that data set, right there, is the mean of the data set. So before I can do anything else, I need to get the mean of this data set. So I'm going to find the mean. The mean of this data set is going to be the sum of all the data points divided by how many there are. Okay? There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 data points here. So it's going to be something divided by 12. And I'm going to take the sum of them. Well, that's 10, that's 20, that's 30. 8 and 7 and 5 is 20, so that's 50. I've got 7 and 7 is 14, so I'm up to 64. I've got a 9 and a 9, that's 18, and an 8. 64 and 18 is 74 is 82, and 8 gives me 90. So it's 90 divided by 12. 90 divided by 12 is 45 over 6. Those both divide by 3. So that's going to be what? 115 over 2, or 7.5. So my mean is 7.5. And now what I'm going to do is I'm going to go ahead and calculate my sample standard deviation. So the easiest way to do this is to make a table. And on this side over here, place your data set. So these are going to be my x's. So my data is 4, 7, 6, 7, 9, 5, 8, 10, 9, 8, 7, 10. Okay. And now I'm going to make a column for all of my deviations, that is all of my x's minus my mean. So I'm going to take every single one of those and subtract off my mean. Now just remember my mean, we already calculated it, was 7.5. So 4 minus 7.5 is a negative 3.5. 7 minus 7.5 is a negative 0.5. 6 minus 7.5 is negative 1.5. 7 is negative 0.5. 9 minus 7.5 is, what is that, 1.5? 5 would be negative 2.5. 8 would be 0.5. 10 would be 2.5. 9 would be 1.5. 8 would be 0.5. 7 would be negative 0.5. And 10 is what we said it was, 2.5. Right? And so what I found there, if I look back at the formula, do you see how that's just this piece inside of the numerator there? Okay. And so now I have to square all of those. So now I'll make another column over here. And then this next column, I'm going to take all those x's minus those x bars, and I'm going to square them. So let's see, I'm going to need a calculator for that. Let's see, negative 3.5 squared. Oops, 12.25. 0.5 squared. 0.25. 1.5 squared. You notice I'm ignoring the negatives because I really don't care, because they're going to be positive. That's going to be 0.25. That's going to be 2.25. 2.5 squared. 525. 625. 6.25. 0.25. 6.25. 2.25, 0.25, 0.25, and 6.25. So now I found all the squared. So let me make this go away. So in terms of the formula, I've done up to here. Now I need to add all those up. So I need to add up that column, take the total of that. Well, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.25s. 12.25s is 3. 12 quarters is $3. Now I'll add up the whole numbers. That's 12, 13, 14, 15, 16. 16 and 6 is, what was that, 22. 22 and 6 is 28, 29, 30, 36. And so another 36 for a grand total of 39.00, but 39. Okay. So now I've added up this entire numerator. So now I need to divide it by n minus 1. So I'll take that 39. I'll divide it by n minus 1. So let's see, we're 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So n is 12. So I'll divide by 11. So 39 divided by 11 is going to be what? 3 and 6/11ths. Okay. So now what have I done? Oh, I've done everything inside of the root. Now I need to do the root. I need to take the square root of that. So I'll grab my calculator and I'll say, okay, calculator, what is the square root of, let's see, 39/11ths? I guess I'll write it like that so I don't get it wrong. And I get 1.88. And so I get that my standard deviation is 1.88. Okay, so now I just did a whole bunch. I did a whole bunch of calculations, but let's take a look at what we're trying to say here. Right? I am attempting to describe this data set without just handing you that pile of numbers. And so far, here's what I know about it. I know that the mean is 7.5. The middle, the typical, the center of this data set is 7.5. And I have a standard deviation of 1.88. Now 1.8 is a fairly large standard deviation if the middle is only 7.5. Think of this in terms of money. Suppose you're out for dinner and one meal costs $7.50. Okay, but on the menu the variation on average was 1.88. And what that would attempt to tell me is that, yeah, there might be a meal on there that's $7.50, but the next one might be $9.38, one standard deviation above, so $7.50 plus $1.88, $9.38. Or it could be $1.88 below. So what would that be, like 5 and change? $5.62 or something like that. And so there'd be a fairly big amount of variability, a fairly large variability in that data set. Now you can also see it because when you look at this actual data set up here, we're going from 4s and 5s to 9s and 10s. That's pretty spread out. This is not all tightly clustered together. It isn't all right tightly packed around 7.5. It's kind of spread out. And the standard deviation being a relatively large number is trying to say that. Right? Now, I know here's the other thing you're thinking, man, that's a lot of work. Is there some way that we can do this without having to do all that work? There absolutely is. The calculator can do all this for you. We don't need to do what I just did. We could have just gone to our calculator, edited our data. Let's get rid of this because I don't need it anymore. Type in our data set 4, 7, 6, 7, 9, 5, 8, 10, 9, 8, 7, 10. There's my data set. Stats, calculate, one variable stats. Get rid of that because there is no list 1 anymore, so let's just delete that out. Okay. Calculate it. You'll see that I got a mean of 7.5, and you see my standard deviation right there at 1.88. Same as I got by hand. Okay. Feel free, if you want, to do these by hand, but I just want to take a look at what I had to do this by hand, right? I had to perform one calculation correctly here. I had to perform 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 calculations correctly at this point. 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25 calculations correctly. 26 calculations correctly. 27 calculations correctly. And then when I took the square root, 28. So you have to do at least 28 calculations correctly to get this answer. And this is again, big picture, a relatively small data set, only 12 data points. Double the size of this data set, and you're going to at least double the number of calculations. Right? So please don't do these things by hand. I wanted to show you what was happening and how the calculation is being done, but really let technology work for you. Let the calculator do the work for you. It can find the standard deviation. It can find that mean. Okay? Now, let's take a look at what the standard deviations mean. Right? The standard deviation attempts to describe a measurement of the typical amount that an entry would deviate from the mean. So it's trying to average those deviations. Right? I have 3 graphs here. They all have the same mean, but they all have different standard deviations. The first one has a standard deviation of exactly 0. Now, what a standard deviation of 0 means is there is literally 0 deviation from the mean. And that picture shows that. Every single data point is just a 5. Okay? Be like open up your wallet and only having $5 bills in there. And that's it. Well, the average is 5 and there's no deviation. This middle one has a somewhat larger standard deviation, and you can see that in the graph as the data starts to spread out. It's still kind of clustered around the middle a little bit, but there is some spread to the data, and it shows up in my standard deviation. Now, as the standard deviation gets larger, the spread gets larger. Right? It actually is possible to have a standard deviation that is larger than your mean. It's not common, it's unusual, but it is possible. So bigger standard deviation, more spread out data, smaller standard deviation, less spread out data. Right? There are lots of applications in business and economics where we attempt to minimize this. In production, we almost always want to try to minimize our standard deviation. Imagine that you are making bolts at the bolt factory, and your job is to make 5-inch long bolts. What does that mean? Well, that means you made a bunch of bolts and they were all exactly 5 inches, no variability, very, very good, very, very small standard deviation. Here, what's happening? Well, my standard deviation is getting kind of big, which means that I've got some bolts that are as small as 3 inches and some bolts that are as long as 7 inches. What's my job? My job is to make 5-inch long bolts, and I'm doing a horrible job of it. So I need to try to some way minimize that standard deviation, because that standard deviation in this sense is an error in what I'm doing, right? And this would be insane. I'd be out of a job if I was supposed to make 5-inch long bolts and I had something like that going on, because the bolts are nowhere near 5 inches long. All right, so standard deviation. Our job is to use the standard deviation as a measure of spread, a measure of variation in a data set. It is a single number that tries to describe it. The smaller, relatively speaking, the smaller the number is, the less there is, less spread in the data set, the less deviation that exists. Right? Ideally, I guess if I was trying to make 5-inch long bolts, I'd want my X bar to be 5, and I want my standard deviation maybe be like 0.1 inches, a 1/10 of an inch one way or the other, or maybe 1/100 of an inch. Depends on who I'm making these bolts for. 1/10 of an inch, Walmart, 1/100 of an inch, maybe NASA, something like that. It's got to be accurate within 1/100 of an inch. Okay. Some quick observations and then we'll end the video. The standard deviation is a measure of variation that is about the mean. So if your goal is to describe a data set by using the mean as your measure of center, then your measure of variability, the measure of variation, is going to be the standard deviation. They have the same units. So if your mean is inches, your standard deviation is inches. If your mean is feet, your standard deviation is feet. If your mean up here is days, our standard deviation is days, because this was the days that it took to recover from a concussion. Right? S is 0 means there's no variability. The bigger S is, the more variability, the more spread out the data is. Right? All right, we'll end this video here. We'll come back in the second part of this video. We'll take a look at finding the sample standard deviation from frequency distributions in group data. I'll see you for that one soon.